So good evening, everyone. Thank you for joining me on this physics talk, which is the last session of the day. So I can imagine you're all looking forward to the party, which takes part right after this talk. So thanks again for coming. I will try to entertain you with some physics stuff. I only have 30 minutes this day, and I had to select some things which are easy to explain just in a couple of minutes. So I will be talking to you today about 2D physics and some key tips and tricks concerning performance, as well as 3D tips and tricks. And I'll be covering only a few selected topics, so it's not like a full session. So first, I will start with 2D physics. And I'd like to start with talking to you about performance aspects. So one such performance consideration is to understand how Box2D works with transforms. And there are several important things. So first, when you have a game object and then there is a bunch of colliders attached right down in the hierarchy, Box2D doesn't keep track of the transform, and all child colliders just live in the space relative to root rigid body. So whenever you change a transform of the child collider, we have to rebuild the child collider, so it takes performance. And another important thing is that Box2D was designed mostly in a way that it expects most of these objects are immutable. So you set the parameters once, and then you never change them. Of course, we have exposed all of the properties in Unity, but the cost is that when you change a radius of circle collider, for instance, we have to rebuild the collider from scratch. Another consideration is static colliders again. In Box2D, when we create a static collider, it's attached to a single root static body. And when you change a transform of a static collider, we have to recompute the transform and bake it in again, because they all live in this single space. Another thing that helps you increase performance is to make sure you all use the non-allocating physics query APIs. That is, if you have an inner loop and you want to optimize it, just make sure you create the buffer which Box2D uses to output all of the context for raycast, for instance. It's very important because otherwise we would allocate this buffer every time for you, and then it goes away and it introduces a lot of GC pressure. We have this in the pipeline for 3D physics as well, but it's not yet ready. But at least make sure you use it in 2D. Then, when you have a game with a character controller, a feature that is used pretty often is you need to implement character jumping, and you need to check whether your character is grounded or not. And previously, the typical way to do that was to simply run a separate query like raycast or another thing like a shapecast to figure out if we are close enough to the ground. And in 5.0, we introduced new APIs for that. You can simply call collide is touching, or there is rigid body 2D is touching. And this function is pretty cheap because it doesn't do any queries. It simply looks into the internal database to see if there was a contact registered. So it's as cheap as possible, and it doesn't introduce any GC pressure, so please use this. And the second form of is touching layers, which is especially useful for the purpose I described, as in checking whether a character controller is on ground or not. If you mark all of your ground colliders as one layer, then it's just one call, which doesn't require to run any queries at all. Next, we expose additional ways of controlling degrees of freedom for 2D rigid bodies. So previously, we had fixed angle property, which basically restricted all rotations. So in Phi 1, we expose freeze position and freeze position, freeze position X and freeze position Y. And yeah, we also replace fixed angle with freeze rotation. So it's now symmetric to 3D API. We also have a few interesting things that are coming really soon. And first, I'd like to let you know that we are introducing 4 new joint types that are fixed joint, friction joint, and relative joint, and target joint. So fixed joint is obviously a new type of joint that helps you bring objects together. And there is actually a spring internally, so you can actually set how stiff you want the spring to be. It can be either completely rigid or not. Then there is a friction joint, which applies obviously linear and rotational friction. Then relative joint is useful to keep orientation of 2 bodies together, aligned. Then the target joint is a simple joint to attract your object towards a goal. But there is one more thing. Here we go. It's a buoyancy factor. And the buoyancy factor is the way you now work with liquids. So the buoyancy factor figures out the floating force, the flow force, and the drag force, and adds them all together and applies to rigid bodies 2D. So you can have several liquids on one frame. They all compute the submerged parts of rigid bodies. We make sure we cache everything we can so that our implementation of liquids is as fast as possible, so you can have a lot of colliders floating and moving around. I will show you later that you are not constrained to simple boxes for liquids, and you can also use other types of colliders, really. And they all introduce, as I've said, floating point and then floating force and flow force. So you can, animate things and have them floating and hanging in the water. This whole technique computes forces, and that means it works perfectly with other kinds of joints. So you can have a body which floats in the water, and then you can attach other rigid bodies to it using simple joints. Our implementation is as efficient as possible, and you can have a lot of objects floating, and you can change all the properties runtime. So for instance, here we change the level of the water runtime, simulating the effect of filling the cup with liquid or draining it completely, and it's all working real time. So here you can see we have just enabled the fluid flow force, and they all stack up together, and there is also the floating force applied, so they are being pushed out of the cup, and they all stack and flow right away from the cup. Here we go. Here is a quick demo that shows that you can use other kinds of colliders and mark them as liquids. And when you have a collider that doesn't touch liquids, there is absolutely no excess computations going on. And we update the submerged area only when we understand that the collider is touching something. And if it's not, then there is no calculations at all. Here you can see that we can change the water level in all kinds of colliders, simply real time. So that is buoyancy factor. Right. So this is all about 2D physics. And now I want you to stop on a few 3D physics updates. So we've been working on 3D physics for 5.1, and we've been fixing a lot of stuff. So I think it's fair to say that we've been mostly fixing bugs that were introduced in 5.0. But we also managed to put a few interesting things. So first, we have improved performance for triggers. Like we have a much more efficient implementation for on-trigger stay, which was causing a lot of regressions, especially on consoles. Then we have better error reporting when it comes to recreating Mesh Collider. So as you know, previously when you set the incorrect flags on the Mesh Collider, like it's concave, but then you want to set it as trigger, there will be completely no errors. And if you have a big project, it is pretty challenging to find such a Mesh Collider. So we have fixed that, and now you can get a full path, and yeah, it's now actually helpful. And another thing is that we have a completely new implementation of hinge joints, which now works nicely with changing configurations both from scripts and from the inspector, because the previous implementations had a lot of corner cases. But that's not what I'm going to talk to you right now. I have selected two areas which receive a lot of questions, and that is joints in generic and WheelCollider. So let's go for that. I don't know, clicker is not working. So as far as I've seen, there are three areas which introduce typical issues. So first, you can run into issues when you're dealing with fast-moving bodies. Then there are a couple of issues because of the locked rotational degrees of freedom. And then there are a few special cases when you use ragdolls. So now I will be going through those and explaining what are the best practices to address those. So first, fast-moving bodies. There was one typical example reported on the beta groups during the 5.0 testing cycle, and that was a game about an alpine skier going down the slope. And the problem with the skier was that they had a mock character controller, which was simply, well, a couple of rigid bodies just racing down the track. And then when it comes to a state where you can't really avoid collisions, they converted the mock character controller into ragdoll, and then it was expected to behave in a physically realistic way. But actually, the main problem with this kind of configuration is that if you convert late enough, then physics would push a ragdoll into obstacles. They had trees and fences and such kind of stuff. And if physics finds a body part inside the colliding state, it will push things from the obstacles and then breaks joint constraints. And that in turn results in explosions. So the first thing, if you have a really fast-moving object and then you convert it to a ragdoll, like in this particular project, is to make sure you convert to ragdoll as soon as possible. And please remember that there is a one-frame delay in physics from the moment when physics is able to detect contact to the moment when physics can apply forces. So at really high moving speeds, it can become pretty challenging to, keep your character in place without joints stretching and flying around. Another thing is to increase the contact offset. So the contact offset is the distance when physics starts generating contacts and starts to update them every frame. So when physics sees that the pair of colliders are closer than the sum of their respective contact offsets, then it starts generating contacts. And by default, we have a really small value which suits a lot of cases, but not the fast-moving objects. And you need to make sure that your fast-moving object doesn't have a contact offset of just a few millimeters. Next, there are a couple of issues rising from constraining rotational degrees of freedom. And here you need to understand that this is implemented as setting infinite inertia tensor components So for instance, if you constrain rotations around y, then we simply set infinite inertia component around y. And we pass this to phys. And then the solver can really understand that, all right, there is an infinite inertia, so I have to apply infinite torque to move it around, but I won't do so because nobody wants an infinite torque. And that works really well in most of the cases, but sometimes in really challenging configurations, this actually introduces explosions when physics actually tries to apply infinite torques. And if you see this happening in your project, simply disable the process which introduces the infinite torques. This is called preprocessing, and we have a flag on joints. So simply disable this, and that's all. With ragdolls, one important consideration is that you need to have all of your body parts with the same mass. It's pretty intuitive to have the masses different, but then if you look at how physics keeps the joints together, it actually figures out the force and then applies this force to both constrained bodies. And if you have different masses, it's obvious that you will get different accelerations. And this is exactly what results in stretching your limbs. That's especially, noticeable when you work with explosions, like a character, walking over the bomb and then it flies up. So here we have a projection, which is an algorithm that can simply bring everything back, but it's not physical and it can gain energy or lose energy, so use it with caution. Now to WheelCollider. So the story with the WheelCollider is that sometimes it's not really easy to start using WheelCollider because we have those suspension settings and they really depend on the sprung mass. And I prepared a project called Easy Suspension, and I made it available to, beta groups. I posted it on forums, and then I posted it directly to users and on Twitter and on YouTube channel. And I will be showing it again today. So Easy Suspension is a project that creates those box-shaped cars. And why is it useful, really? It is useful because it creates those cars just in a couple of clicks. So you only specify how many axles you want, and then you specify mass and a few geometric parameters, and you get this car which already works. You just hit generate and hit play, and it works. And you can start right from there. I mean, you can simply replace the box with your custom geometry. It'll work, and then you can tweak parameters. I will be talking about that just in a couple of minutes. And you can, play with the parameters and get unusual cars. So I had a lot of complaints about WheelCollider being unable to work with more than 4 wheels and cars that weighed not 1.5 tons, but somewhat different. And here you can actually try different masses. And I will explain to you why Easy Suspension is able to get different masses and you don't get this working with the plain WheelCollider. Here we go. So this is a simplified model of the suspension that physics uses, actually. So right on top, we have the sprung mass. And we also have a spring and a damper. So the sprung mass is actually the portion of the total car's mass that is supported by this given wheel. So you don't actually set it explicitly. We figure it out for you automatically based on the location of the wheels, on the mass of the vehicle, on the amount of the wheels, of course. So the spring stiffness and spring damper parameters really depend on the sprung mass. And if you look at the default settings we have on the WheelCollider, it is actually configured to support just a typical family car that weighs 1.5 tons and has 4 wheels, and all the weights are distributed evenly. So one way to fix it is simply use another model. which is used in easy suspension. And then it takes something that looks a lot more academic, but if you spend a minute or two, you will understand that it's actually a better model. So this is all about natural frequency and damping ratio. So easy suspension lets you to set natural frequency and damping ratio, and then it works out spring stiffness and spring damper from those values using the formulas right there. And if you use spring stiffness and spring damper, you have to configure those for each individual wheel. And every time you add a new wheel, you have to change those parameters. If you change the location of the wheels, you have to change the parameters as well. But the good thing about natural frequency and damping ratio is that you can set them for the whole vehicle, and it doesn't depend on the mass. I wanted to show you a little graphic that would explain what the damping ratio is, because the formula is pretty scary, but actually it's easy to see on this family of curves. So the curves are basically the trajectories of the center of the wheel. And you can see that the blue curve corresponds to the damping ratio of 0, and that means the oscillations are totally free and they never settle down. But if you increase the damping ratio to 1, for instance, then you have no bounces at all, and simply it goes up to the rest position and never bounces. So obviously the most interesting values are somewhere in between 0 and 1. And this is also, like a visual way to see what's going on when you change values. So this is a slide showing you the values that are typical for a real-world vehicle. So for a typical family car, you would have natural frequency of around 10, like 8, 9, 11. It works good. Then the damping ratio would be around 0.7, 0.8, like this. So again, you simply set natural frequency and damping ratio, and then you don't depend on the sprung mass. So that's good. So once I got this easy suspension demo, I wanted to get creative and try more complicated configurations. So I got this simple scene with a car train from connecting a few cars together. So I will just show you how it is assembled internally. So I already had created the first car. Then there is the second one, which I simply created using the wizard. I set the number of axles to simply 2. And I also changed the default mass to 300 kilograms because I think it makes sense for the smaller cars to weigh less. Then I hit generate. Then I added a stretched cube, which I imagine to be a bar that connects two cars together. It also takes two configurable joints. One is used to attach the bar to the front car, and the second one is really used to attach the bar to the rear one. And that's all. Then I hit play and it almost works. I have added a simple line which rotates the front wheels of the rear car so that it corresponds to the direction in which we pull it, actually. I will show you a video why is it important. But that's basically it. Then I copy and paste, and I can get as many cars following the main truck as I want. Another way this project can be useful is to quickly try to add simple dynamics to your vehicle models. So in this particular case, I downloaded a model of a military truck, I guess. And then I created a box-shaped car with 3 axles. And then I had to simply, stretch the collider, remove the, box renderer, and then also adjust positions of the wheel colliders, and that's it. Then I hit play, and it all works. And here is a little video showing how it really works. So this is the kind of behavior I got right, after a few clicks from going from the box-shaped car to this kind of truck. So it has, all you would expect from a simple car. It has, graphics wheels following physics wheels. It has friction. It has suspension. Everything. This is actually the kind of a car that you get directly from easy suspension when you hit generate. So you hit generate and you get this. So it's able to steer, it has a primitive controller, and it also has a component which would update all the WheelCollider settings when you change natural frequency, damping ratio, or mass. Here I got a car that carries a flag. So here it is. And this is why it was important to add the single line change to rotate the front wheels of the cars following the main one. This is because I can get, the behavior like this. It's pretty much like you see in the airport when your baggage is being transferred from the airplane. Yep. So here it is. So I think that's mostly it for this, half an hour physics session. I hope you enjoyed it, and feel free to contact me using email or post on Twitter or comment on my YouTube channel. And also catch me at the Ask the Experts area, or, I don't know, reach me some other way. I hope you enjoyed it, and thanks for attention, thanks for coming, and let's see if there are any questions.